We're moving on now to section 12.5, which we'll have together with 12.6 is a type of application problem that's very important for calculus. And those of you who will see calculus in other courses, this is one of the ways in which it's likely to come up. The idea here is when you have a problem that describes a quantity, your goal is to maximize or minimize that quantity. So for example, if we have a profit function, we would want to try to find a production level that maximizes profit. If we had a cost function, we would want to try to minimize cost. So in terms of general calculus, the idea here is that we're going to be finding the location of the very highest and very lowest y-coordinate on a graph, and then we'll be applying that idea to some specific types of problems. So in 12.5, we first learn a procedure for doing this, and it uses everything that we've talked about so far, but it does actually have some shortcuts to it because of some general facts about graphs. If you haven't done this already, it's a good idea to find this page of the book that I'm showing now. This is page 673 on my ebook, and there is a little box here with a procedure for finding absolute extrema on a closed interval. Extrema just means maximum or minimum. So the largest y-coordinate and the smallest y-coordinate over a closed interval. So this is a nice thing to print out. It's the procedure that I'll use, and I'll refer to step 1 through 5 as if we're looking at this, even though I'll put it off the screen while I'm working on the problem. The idea of the theorem is that on a graph, where's my pen? Oh, there's my pen. On a graph, when we have a smooth function on a closed interval, so this is a smooth function, there are no gaps in it, and we have a closed interval, meaning that we're only really paying attention starting at 0 and ending at 5. So even though the graph is shown larger than that, we don't really care about anything other than what's going on the window with x equals 0 and x equals 5. So we can see on this window that in this window the graph does have a lowest y-coordinate. It's right there. So that's the absolute min. And this point here, the graph's coming back down. So this graph is neither the high point or a low point. It's just a point somewhere in between. And here, this is the very highest y-coordinate that we ever see. So this is going to be our absolute max. So if we were looking for a max or a min, these extreme values of this graph, then the smallest y value we see is y equals 0. And so I would say the absolute min is f of 0 equals 0. In other words, this tells us the x-coordinate, and this tells us the y-coordinate of the smallest y-coordinate that we see. And for the max, the choice isn't on this screen, but the absolute max is at f of, looks like 1, 2, 3. F of 3 is equal to 5. So when x is 3, the y-coordinate is 5, and that's the biggest y-coordinate that I ever see, again, on this in this little window. The theorem says that when you're looking for the extreme values, you only have to look at the endpoints. So in other words, here x equals 0 and x equals 5, those are two places that you might see an extreme value. And you have to look at any kind of critical value, so a place where the first derivative is 0 or undefined. And that's it. Those are the only places that you could have an extreme value. So the process that I talked about, that I encourage you to copy down, basically says make a list of all the x's that you could see an extreme value, and that will be taking x equals 0 in this case, x equals 5, and x equals 3. Those are the only three places that you might see an extreme value. And then you're literally just going to check. You're going to check the y-coordinate for each of them. So if you have a list of all possible places that the extreme value could occur, and you check the y-coordinates for each one of them, then the biggest of those y-coordinates is going to be your absolute max, and the smallest of those y-coordinates is going to be your absolute min. So it's easy when you're looking at a graph. Let's look at a problem where we don't have a graph in front of us and see how calculus can tell us where these values are going to be, even if we don't have a graph. So I'm interested in this function and this interval. So this is a continuous function, so I don't have to worry about the graph jumping around. My first step, what they call step 2 in the book, is to solve f prime of x equals 0. Now to do that, we first have to know what f prime of x is. Right? So first we have to find f prime of x. And in this case, f prime of x is going to be 2x minus 6. That's just my derivative of the function. Set it equal to 0 and solve for x. In this case, x will be 3. So that's the only critical value that the graph, that the function has. So, so now in our possible list of x values, the endpoints, which would be x equals 2 and x equals 5, those are the two endpoints that I'm looking at. In other words, that's the left-hand side and the right-hand side of my window. And I will include here, among all possible x values, any critical value that's actually in the window. So x equals 3 would count here. It's possible that there are critical values that we found in step 2 that aren't even in the window, that aren't even between 2 and 5. So we wouldn't include those. We only want to include stuff that's between 2 and 5. So this is a complete list. Those are all the possible x coordinates that you could have where you might see the largest and smallest value of the graph. So what is the largest and smallest y coordinate? Well, all I've got to do is find the y coordinates for each of these values of x. So for each value of x that I have in my list of the possibilities for extreme value, I'm going to calculate the y coordinate. So we all have f of 2 is 2 squared minus 12, so it was 4 minus 12 minus 4, so that's negative 12. F of 3 is 9 minus 18 is negative 9, minus 4 is negative 13. And f of 5 is 25 minus 30, that's negative 5, minus 4 is negative 9. So this is the largest, and this is the smallest of all of those values. So I would say the absolute maximum value of the function, that's the maximum y coordinate, is negative 9, and that happens when x is 5. And the next line will ask me about the minimum, and I would say the minimum is negative 13, and that happens when x equals 3. So this leaves us with problems where we are still trying to find absolute max or absolute min, but we don't have a closed interval, so it doesn't fall into the category that our procedure can apply to. The general idea is to try the same thing, and if you need to draw a sign chart to get a sense for what's going on, that's fine. But in each case, you'll sort of have to just really think about the shape of the graph that you're getting from the derivative information. So, for example, in this problem, if I were setting off to try to find critical values, I would do that by finding the derivative first, which in this case would be 8x cubed minus 72x squared. And again, I'm trying to find where that's equal to 0. So I would factor out an 8x squared, leaving me with x minus 9. And so either x equals 0 or x equals 9. Now, x equals 0 is not actually on the window that I'm interested in. I'm only interested here in x's that are between 0 and infinity, and we're not including 0 in that list. So this is the only critical value. Now the question is that a relative, is that an absolute max, an absolute min, or neither? Well, we could draw a sign chart and sample and get some f prime information on there. That would be considered the first derivative test to deciding if this is a local max or local min. Or we could use the second derivative test. In this case, the second derivative is very easy to calculate. So that's actually your best bet. If the second derivative of your function is easy to calculate, then you'll be able to get a lot of information from the second derivative and save yourself the trouble of having to draw a sign chart. The second derivative in this case is 24x squared minus 144x. Now, I'm not trying to solve whether it's equal to 0. I don't really care. What I want to know is what's happening at 9. Remember, 9 was the only critical value that I found. So if I put 9 in here for x, I'll have 24 times 9 squared, which is a pretty big number, minus 144 times 9. And you can check that on your calculator, but the point is that that is positive. That's a positive value. So therefore, the function actually has an upward concave shape at x equals 9, and it's horizontal. So we know the graph is horizontal, and it has a concave up shape. So in your mind, if you can picture a concave up shape and this horizontal tangent line, the only possible conclusion is that that is a minimum. So because we have this shape, we know that this is a local minimum. And since that's the only critical value that I have on this interval, if it's a local minimum, it means that it's a low point just relative to itself, but the graph never comes back down again. There's never a point where the graph changes direction again. That's the only critical value. So therefore, at 9 here, we must have an absolute minimum. And again, because there is no place where the graph turns over again, then there is no absolute maximum. So there's no absolute maximum, but the absolute minimum occurs at x equals 9.